What do I do? Click again. Click what? Click. Okay, can we get rid of that part? Okay. All right. So with the property that users whose keys do not satisfy the challenge policy should not be able to decrypt. And in fact, this property should hold even if users are colluding. Namely, if a set of users who individually are not able to decrypt the ciphertext, they should not be able to combine their keys together and decrypt the challenge ciphertext. As I have described it here, there is a single authority that is responsible for issuing keys to all the different users in the system. However, in the practice and in the real world, things are oftentimes more fragmented. It might make more sense for different authorities to control different attributes. In the university-based example that I've described here, it might make sense for different universities to manage the attributes for the different users within their respective domains. This is the notion of multi-authority attribute-based encryption, or multi-authority ABE for short. So in a multi-authority ABE scheme, anyone can become an authority. And when an authority comes online, they basically publish a public key along with a set of attributes that it controls. And importantly, in these systems, we require that there is no interaction or coordination between individual authorities. Ciphertexts are still associated with different policies, where here the policy is expressed as a function of a set of attributes and the authorities that manage them. So a recent line of work have shown how to construct multi-authority ABE for different policy families, as well as different cryptographic assumptions. Starting from the work of Liu and Waters, for instance, we have constructions for Boolean formulas from bilinear map assumptions. And very recently, a work of Dada, Komargatsky, and Waters shows how to construct multi-authority ABE for the class of conjunction policies from the plain learning with errors assumption. If we look at all of these existing constructions, however, all of them are in a random oracle model. And so the natural question that we ask in this work is whether we can hope to construct multi-authority ABE schemes without relying on random oracles. And here I'll preface that we also will avoid strong general purpose assumptions like extractable witness encryption or indistinguishability obfuscation. In fact, we ask, can we show that one of these existing constructions is actually secure in a plain model with a suitable instantiation of the underlying hash function? And that's exactly what we do in this work. So we show that if we take the construction of Dada, Komargatsky, and Waters, and we instantiate the hash function with a concrete function, we actually can argue security in a plain model, but under a stronger version of the LWE assumption, this recently introduced evasive LWE assumption. I think an interesting property of our particular construction is that the hash function that we use here is actually not a random looking function at all. The hash function is actually a subset product of low norm matrices. So here D0 and D1 are public matrices. And just by taking a subset product, we can show that this scheme is actually provably secure under this evasive LWE assumption. Now, granted, evasive LWE is not a standard assumption, but I think it still provides a useful evidence that shows that this approach is still sound and plausibly gives a secure instantiation. And it leaves open the very intriguing problem of whether we can hope to prove the security of this construction with this particular instantiation of the hash function from the standard LWE assumption. So before I launch into the details of our construction, let me give you a flavor for why the random oracle has been helpful in constructing multi-authority ABE schemes. The key challenge in proving the security of multi-authority ABE is handling collusions. Namely, how do we ensure that different users who have different sets of keys that are individually not able to decrypt the ciphertext cannot somehow combine them together to decrypt? In a single authority setting, this is handled by using correlated randomness to generate the keys associated with a particular user. So the same authority, when it gives out the keys for a particular user, they're going to use a common randomness to prevent mixing and matching of keys across different users. This kind of approach is difficult to implement in a multi-authority setting because different authorities have to act independently when generating the keys for a particular user. So what is done there is that we associate each user with a global identifier, denoted GID, and the keys are generated using correlated randomness, and the correlated randomness is derived, what's under here, it's derived by hashing the GID using some hash function H. And in the security proof, we actually need to model H as a random oracle. So now let's talk about our particular construction. So let me start by describing a simple construction. This is a simplified version of the construction of data Kolmogorski and Waters. And for simplicity of exposition, I'm going to assume that every authority just controls a single attribute in the scheme. So we have 3 authorities. Each of the 3 authorities will publish a public key. The public key in this case just includes two random matrices A and B, as well as a random vector P. Each authority will also have a trapdoor associated with it. This will be a trapdoor for the matrix A. And if you're not familiar with lattice trapdoors, that's perfectly fine. All you need to know is that a lattice trapdoor allows us to sample short solutions to the linear system defined by A. So if you have a trapdoor for A and a target value Y, you can sample a short X such that A times X is equal to Y. So now let me tell you how the secret keys are generated in our particular scheme. So when the user with a particular GID goes to authority 1 and requests a secret key for their attribute, what the authority will do is it will first hash the GID to obtain some random vector R. And then it's going to use this trapdoor to sample a pre-image K, so a sample a short solution K, such that A times K is equal to P plus B times R. So this is the key equation or the key invariant that we will use in our particular construction. If the user now goes to authority 2, they do exactly the same thing, but with respect to authority 2's public key. The key idea or the key insight is that R here, this thing that's derived by hashing the GID, is the common randomness that is tying together the different keys to this particular user. Next, let me tell you what the ciphertext looks like. So suppose I want to encrypt to the policy that's that you have the key for authority 1 and for authority 2. What the ciphertext structure is as follows. First, we're going to sample our LWE secrets and just compute an LWE instance with respect to each of these public matrices. And again, for ease of exposition, I'm going to use a squiggly underline to denote the error. So I won't have error terms floating around. Hopefully, this will simplify the description. And I'm going to do the same thing with the second set of matrices B1 and B2, except instead of publishing them directly, I'm going to sum those two together. And I'm also going to do the same thing for P. So I'm going to sample LWE secret and just compute LWE instances with respect to all of these components. Why I do this will hopefully become clear when I talk about correctness. So let's see how we can decrypt. So here we have our user. User has a secret key associated with authorities 1 and 2. We can view this vector K, the secret key, as a way to recode the LWE instance with respect to A to an LWE instance with respect to B plus P. So that's exactly what we're going to do first. We're going to take the part of the ciphertext, multiply by the key, and then we get an LWE instance with respect to BR plus P. Now notice that what the user can do is it can take the other components of the ciphertext, combine them together, and subtract and recover an encoded version of the message. Okay, so this is how we can argue correctness of this construction. What's more interesting is the security analysis. So let's see what we want to show. So we have a collection of public keys. We have a set of we have a ciphertext that's associated with some policy. Here the policy is authority 1 and authority 2. And the strategy in arguing security in many lattice-based IBE schemes is we're basically going to argue that this ciphertext here is pseudo-random, provided that none of the keys here actually satisfy the decryption policy. So this is easy to do if the adversary has no secret keys. Then this is just pseudo-random by plain LWE. But if we also have to simulate keys for certain attributes that do not satisfy the policy, things become more difficult. So in order to simulate these keys, we typically need a trapdoor for A, but then we can't appeal to LWE with respect to A. So previously, data Kolmogorski and Waters, what they show is they model H as a random oracle and rely on a lattice trapdoor sampling lemma to argue security. Here, we can do something similar in our work. We have a more modular approach that allows us to base it on LWE with a polynomial approximation factor rather than a sub-exponential one. I won't delve into the details because this is orthogonal to what I want to say today. What I do want to tell you is how we can use the evasive LWE assumption to prove security of this construction in a plain model without modeling H as a random oracle. So the evasive LWE assumption recently introduced by Wee and Zabari basically says the following. If LWE holds with respect to a matrix A concatenated with a matrix P, then LWE holds with respect to the matrix A, even if you're given a short preimage of P under A. So essentially what this is saying is that if I give you this A inverse of P thing, the only thing that you can really do with it is you can multiply with A. And if you do that, then you're going to get something that still looks pseudo-random. So this is the evasive LWE assumption. And let's see why this is helpful for us. Well, if you look at the things in the security reduction that we had trouble simulating, it was these preimages. Well, the evasive LWE assumption says, well, I will just give you these preimages for free, provided that you can reason about the distribution when multiplied by the secret S. So instead of reasoning about how to sample short preimages, I now only have to reason about pseudo-randomness of a particular distribution. So it now suffices to show that S times this P plus BR term is pseudo-random. So the question then is, how do we design a hash function H to ensure this property? And here the main idea is quite simple. We're going to define H to basically compute a subset product of public no-norm matrices. Why do we do this? Well, a very classic and beautiful result by Fonet, Louis, Montgomery, and Raghunathan show that this is actually a pseudo-random function. And so by the BLMR analysis, we can show that the evasive LWE precondition holds. And so now under the evasive LWE assumption, we can simulate the secret keys in our security reduction. So just to summarize, in this work, we show how to construct multi-authority ABE for class of conjunction policies. We can prove security under LWE, plain LWE, with a polynomial modulus if H is modeled as a random oracle. And if H is not a random oracle, but a subset product of short matrices, we can prove security under the stronger evasive LWE assumption, but in a plain model. So let me leave you with two open questions. One is, can we try to improve security of this construction just from plain LWE without relying on random oracles and without relying on evasive LWE? And more generally, can we try and get lattice-based multi-authority ABE for policy families that are more expressive than conjunctions? From bilinear maps, we can support general Boolean formulas, but here we only know how to support conjunctions at the moment. And with that, I'll conclude. Thank you.
So thank you, David, for the wonderful talk. So are there any questions in the audience?
So is the security equivalent to evasive LWE? Can you show that's necessary?
No, so that's a great question, but we don't have any implication in reverse direction. So it is plausible that this construction you can actually prove secure from LWE. This does not imply evasive LWE, at least as far as I understand.
Okay, yeah, thanks.
More questions? If not, maybe meanwhile I can ask a question. So from my understanding for bilinear maps, it's really important to have to model H as a random oracle. So have you guys given a thought that maybe you can modify the construction slightly, bring in bilinear maps and prove those to be secure without using random oracles, but using these evasive LWE type hash functions?
Yeah, that's a great question. Whether we can try and combine the best of both worlds. So using bilinear maps plus lattices to give us constructions. So I don't have any thoughts on that at the moment. It's not something we've considered, but I think it's a fascinating direction to explore.
Great. Any other questions? If not, then we'll thank David again. All right. Thank you, David. Let's get to the next talk. All right. So the next talk is about lower bounds for the number of decryption updates in registration-based encryption. And the talk is by Wei is going to give the talk, and the paper is by Mohammed and Ahmed Raza and Wei.
Okay, so hello everyone. My name is Wei. Welcome to my talk. Today I'm going to talk about lower bounds for the number of decryption updates in registration-based encryption. This is joint work with my advisor, Professor Mohammed Mamdi, who is sitting there. And our moderator Rahimi, who is he's sitting in Europe. Sorry. So our story begins with the classic public key encryption. We all know how public key encryption works. Suppose Bob wants to encrypt a message and send it to Alice. Alice will generate two keys, a public key and a secret key. Then Bob will use Alice's public key to encrypt the message and send it to Alice. Alice will then be able to use her secret key to decrypt the message. Now, suppose Bob wants to talk to other people, encrypt messages to other people as well. He will do the same thing, but with different people's public keys. For example, Christine's public key to encrypt message to Christine, and Susan's public key to encrypt message to Susan. As we can already observe from this picture, a problem about public key encryption is that every time Bob wants to encrypt a message for a new person, he needs to get another public key. And this is just too many public keys. So in order to solve this problem, a new primitive called identity-based encryption was proposed. In identity-based encryption, there is a third party called central authority who generates a master secret key and a public parameter. Now, suppose Bob wants to encrypt message to Alice. He will get the public parameter. He will then use this public parameter together with Alice's name to encrypt the message and send it to Alice. Alice will send her name to the central authority, who will use this master secret key to generate a decryption key for Alice. Alice will then be able to use this decryption key to decrypt any messages encrypted to her using this public parameter. Now, suppose Bob wants to send encrypt messages for other people as well. He will use this same public parameter here with different names to encrypt messages for different people. And the advantage of identity-based encryption is obvious, as there is only one compact public parameter for all users instead of n users, and public keys for n users. However, there is a problem in identity-based encryption, which is known as the Key Escrow Problem. As we can see from this picture, the central authority, who has the master secret key by definition, can generate decryption keys for every user, which give him the power to decrypt everything. And this is just bad. So in order to address this problem, a new primitive called registration-based encryption was proposed. And roughly speaking, in registration-based encryption, every user will generate their own public key and secret key. They will then send the public key together with their identity to this third-party key curator, who will then publish a compact public parameter, which will function in a similar way as the public parameter in identity-based encryption. Note that in RBE, every identity will generate their own secret key, which makes the third-party key curator basically a public coin algorithm that has no secret state. Okay, so more formally, in RBE, users will come one by one, and after each user is registered, the public parameter will be updated. So for example, let ID1 be the first user. After ID1 is registered, public parameter 1 will be generated, and then more users will come and be registered. Then user ID I will be registered, and the public parameter I-1 will be updated to public parameter I. Now, suppose a user has public parameter K, which is basically the public parameter generated after K users have been registered. We'll be able to use this public parameter K to encrypt messages for any identity that has been registered until this moment. So basically any ID I where I is smaller than or equal to K. And then this ID I shall be able to use the secret key to decrypt the message. However, from time to time, the decryption algorithm might actually fail. And when it does fail, RBE allows this identity to get a decryption update from Key Curator, which will help her decrypt the message successfully. This is not ideal, so it is important for us to know how many times this will happen. Now, before I turn to other properties of RBE, let me just briefly mention that the security of RBE is defined in a similar way as that of IBE. That is, no colluding parties can decrypt others' messages. Okay, now there are some efficiency and compactness requirements of RBE that are important to us. Let n be the number of registered identities we need two properties to hold. First, we want the public parameter to be compact, because if we allow the public parameter to be long, then there is this trivial construction where you just concatenate the public keys of every user. And more formally, we want the length of the public parameter to be polylogarithmic of n. Secondly, we want the updates to be rare, because if we have too many updates, then this RBE scheme will be too cumbersome to use. More formally, we want the number of updates for any user to be the order of log n. Note that here we are ignoring the security parameter, even though everything can depend on it polynomially. Instead, we are focused on how things depend on the number of registered identities. There are also some other requirements of RBE. We want the updates to be compact. We want the update generation algorithm and the registration algorithm to be efficient. But for the sake of this talk, these two can be ignored. Okay, so the main question of this talk is about the number of decryption updates in RBE. How many updates do we actually need? Are login decryption updates really necessary? Note that in all knowing constructions of RBE, logging updates are actually required. So our result is that we have found an almost tight lower bound for the number of decryption updates in RBE. More formally, we prove that log n by log n updates are needed in RBE. However, there is a catch here. We need to assume that updates arrive at fixed times. So for example, assume exactly one identity is registered every day. Then after this identity has been registered, it knows exactly at what days in the future an update is needed. However, this property is satisfied by all knowing constructions, which makes it a natural and reasonable assumption to make. And more generally, we prove that if the number of identities is larger than or equal to this binomial coefficient, L plus D choose D plus 1, and there are at most D updates for any user, then the length of the public parameter has to be omega of L. One can check by calculation that our lower bound actually follows from this result. Also, I like to remark that this result actually holds even if some parties get many updates, as long as sufficiently many parties get rare updates. We want to thank the reviewers for asking about this extension result during the review process. Okay, now let me talk about some ideas using the proof. So the high-level steps of the proof are the following. First, we define a DAG based, define a DAG based on the times of updates. Then we prove there exists a structure in such DAGs. And finally, we show how to use this structure to attack successfully using some basic information theoretical tools. So step one, we define a DAG based on times of updates. Since there are n users, we will define a DAG on n vertices, and the ith user will be represented by the ith vertex. So we have a DAG on vertices 1, 2, 3 till n, and there is an edge from I to j if and only if the ith user needs an update after the jth user has been registered. Note that we know this information because we assume that we know when users need an update. Also note that since a user can only get an update after it has been registered, so the edges can only go from left to right. Okay, so step two, we define a useful structure called skipping sequence in such DAGs where the edges are from left to right. We call a sequence of vertices S1, S2 to SL a skipping sequence if for any outgoing edge SIT, either T is close enough, which means it is smaller than the next vertex in the sequence, or it is far enough, namely it is larger than the last vertex of this sequence. Now that we have a skipping sequence, we can remove all these long edges and then divide these vertices into blocks. And we can observe that edges from the first vertex of every block is contained in this block. And then we proved that if G has L plus D choose D plus 1 vertices, and L degrees are smaller than D, then there is a skipping sequence of length L. And the proof is based on induction on D, which is fully written in the paper. So the last step, we show how to use the skipping sequence to attack. We first divide the vertices into blocks, and recall that every vertex represents a user. Then we call a block good if all the keys of users in this block are almost independent of the public parameter SL, which is generated after user SL has been registered. And we can use information theoretical argument to show that if L is larger than the length of the public parameter SL, then a good block always exists. Which means that if we resample fresh keys for identities in this good block and put it next to the public parameter SL, the distribution will be statistically close to the real distribution where you sample everything jointly. And finally, assume block I is good, we can attack on identity S, I, which is the first vertex inside this block. How do we do that? We first sample fig keys for all identities inside this good block. Then, since we know that updates for this user SI will be generated by case inside this block, we can then generate all decryption candidates for this user SI. And finally, we'll be able to decrypt the challenge encrypted for SI using public parameter SL with probability close to that of using real keys and real update. So in conclusion, we have found an almost tight lower bounds for the number of decryption updates in IBE, and the key idea is the characterization of a structure called skipping sequence in DAX. And there is a main question to be answered. Can we actually break this barrier using dynamic update times that actually depend on the value of the registered public keys? And that's my talk. Thanks.
Thank you very much, Wei, for the wonderful talk. So any questions? Yeah, Yevgeny has a question.
So I assume you said log n is tight in existing constructions. You have log n. Assuming it is tight, I'm just curious, what do the graphs, these update graphs look like in existing constructions? I mean, this dependency graph from I to J. I mean, are they like really simple graphs?
Yeah, I'm sorry. Your question.
Well, I'm just curious. Well, I assume this log n is tight, right? This log n that you proved, it is tight, right?
Yeah.
So the existing constructions achieve log n, right?
Yeah.
So what are the graphs? Just out of curiosity, I'm just curious, what are the graphs that achieve log n and for which you think is tight? These update graphs, how does it look like? You know, this I to J, it's like, when do I have to update? Oh, so it's not a fixed graph. I would imagine it's like simple graph. You're saying it depends on some kind of Merkle tree.
Graphs don't look nice, but they look as if we just run a simple algorithm on Merkle tree stage.
I see.
Yeah. All right, any other questions? So maybe just a quick question. The way you guys are assuming things, what about if updates come in batches? I mean, has that been modeled, or can that be modeled as like a separate problem?
I think that's a separate problem.
So, I mean, basically that means the size of each of the nodes that changes. It's not just one user, it will be multiple users.
Yeah.
So even then, it is possible that there might be a different lower bound depending upon what batch size you're working with.
Actually, no, I think. Yeah.
Yeah, I'm saying is like maybe the number of parties that you want to. So the same lower bound will hold. Okay, the batch size will. No, I'm saying that there will be multiple updates, but each update can have a different batch size, like D1, the first number of times, the D2, so on. Like typically you grow an array. If you want to have like array of fixed size, you sort of just double its size each time you want more populated with more entries, something like that. So how does different batch sizes and different updates might affect the total number of updates potentially? Okay, but yeah, no. Thanks again for the question. Maybe we can take it offline. So the next talk is on IBE with incompressible master secret key and small identity secrets. And the talk is by Shruti.
For the introduction. So this is joint work with Nico Dotling, Sanjam Garg, and Mingwan. The motivation for this work comes from this bigger area of big key cryptography, which is in itself is motivated through this class of attacks called exfiltration attacks. So what are these? It comes from the fact that you may have like several secret keys stored on your computer system, which you use for your favorite cryptographic scheme. And they are prone to some form of exfiltration by an external adversary, which leads to essentially leaking out the entire key. So you lose out the security through these attacks. And this in itself is a general threat, which is recognized as advanced persistent threat. It could be that some malware is launched by an adversary, which could be running in the background in your computer. And that may lead to essentially him on a prolonged basis getting information from your system that leaks to the leak of this key. So a solution proposed for this was through this literature of big key cryptography, which is to make the secret key big. Okay? So let's say it's a terabyte long, then the adversary can no longer get the whole secret key just because of how restricted it is, and with time this is not possible. So, and indeed at RSA 2013, like Shami did mention, you know, of the whole fluff, basically what he wants to say is, I don't want to have tiny secret keys because APTs are in general like well-known threats. And so I want my file to be a terabyte long, which cannot be now easily exfiltrated. That's the model for the big key system. And this is what led to the advance of like several crypto systems that were built in this literature. And the model that's used to actually capture this is known as the well-studied bounded retrieval model. So now the adversary is not getting the whole secret key, but instead getting some part of the secret key through a leakage model. And that is the bounded retrieval model. So it's able to, let's say, even get 99% of the secret key. And that we model through the leakage. But in order to do so, the second key feature these crypto systems must retain is efficiency. So now I've blown up the key, but of course, I don't want my other algorithms that use the key to be affected by it. So you want to retain the efficiency of those algorithms. And that's precisely what this says. And that's ensured by basically making them locally access some parts of the key and not use the whole key. So these are the two key features. Several primitives have been built in this big key system, and that includes symmetry key encryption, public key encryption, authenticated key agreement. Coming to the model that we are interested in today would be the public key encryption setup that we're going to look at. So particularly, just like regular public key encryption, you have a public key or secret key. And the public key in itself is usually small. So this is something we don't need to worry about. But the secret key now is going to be the big key that's prone to the exploitation. So the red components mark basically the leakage that you allow on it. And as the second key feature we wanted, really recall, was the efficiency, right? So if you look at the algorithms here, the encryption algorithm itself is okay. It just uses the public key. So this is going to be efficient. But now the decryption algorithm needs to access the secret key, and it cannot just plain access the entire secret key. That would make it inefficient. So what you do is essentially allow some local ciphertext dependent queries. So these are the black chunks are basically the parts that the decryption accesses. And this would be small number of queries. So essentially you would ensure that the decryption algorithm is efficient. Okay, and note this, these are ciphertext dependent queries. Okay, and the security in this model would just say that the semantic security should hold for the fresh ciphertext that are generated post the arbitrary leakage on the SKS event. Why is this? Like, if you don't assume it's only for fresh ciphertext that you can get, because the older ciphertext you can always get a leakage of a single bit that helps you distinguish. So for the older ciphertext you can't guarantee security if you allow leakage prone giving the ciphertext. But there are certain caveats that naturally this model has, and let's look at them. So in these days, like nobody stores secret key in one system. There are multiple devices a user has. You could have an iPad, a smartwatch, and let's say I want to use this for decrypting emails and which have encrypted. So you would have to store your secret key essentially on all the devices because you don't know in advance which part of the secret key is accessed by the decryption. This recall it made ciphertext dependent access to the secret key. So you need to store them all. And this naturally leads to two issues. The first one is, of course, the natural thing that you see is to lead to wastage of limited storage on smaller mobile devices. But the second issue that it leads to is even more like a bigger problem, which is it leads to additional susceptibilities due to leakage that happens through this replication. So particularly if one of my mobile devices lost, you essentially lose the entire secret key and there's no recovery from it. So these are like major issues of this model that you can see. And our proposal to resolve this issue is adapt to the IBE setup for this. By which I mean that now, instead of using just the public key secret key paradigm of the PKE literature, I bring in my usual standard IBE setup where you have this public parameter, which is short, and the master secret key of the IBE would be the large key that is prone to exfiltration. So this is where I allow my leakage. The encryption, as before, only relies on a public identity. It relies on this public parameter and message M. So this is going to be efficient. And we have to worry about now the decryption, right? So instead of in the public key setup, it was using the whole big secret key. But now naturally the IB setup provides something in the form of these ID specific secret keys. So you would have some specific secret keys that are generated according to your ID. Let's say for our example of email, my identities are dates. So if you keep the identities as dates, these would be my essentially ID specific secret keys that are generated. And recall with our goal, we wanted them to be these short, small ephemerals, right? We don't want to blow them up. So this resolves essentially, at least in terms of the model, both the issues that I spoke of, like each of the device would not have to store the entire big secret key. And secondly, like if one of the device you lose out, you're essentially using a specific date. So you can always refresh security for potentially the next state possible. So that comes to that we'll get to in the security model. But essentially as a model, this resolves the two issues that I spoke of. So there are certain challenges in defining security in this model. And before heading into that, let's recall for a quick recap for everyone to be on the same page, the standard ID security. So remember here, the adversary gets essentially the public key, the public parameter, gets some ID specific secret keys of its choice, which it can query at any instant. And in addition, for a challenge identity of its choice, which is different from all the identities that it queried the keygen oracle, it would get the ciphertext C star, which basically hides the message. So that's the security guarantee. And depending on whether the challenge identity is given before seeing the public parameter or after, you define selective auto security. And the definition that we will look at in our setup will be a selective security notion, not the full security. Okay, so in our setup now, recall now you're allowing this big master secret key and you're giving out leakage on it, right? So the adversary gets this leakage. In addition, so throughout this, I would not list, you would also get the keygen oracle, but to begin with, it gets this leakage, right? And then in addition, it would get these additional secret identities that it can query through the keygen oracle. But a first problem that you can notice, one of the key challenge that arises is this leakage is unrestricted, right? It's just bounded in terms of bits, but it can have any part of the secret key, and potentially even, like I said, 99% of the key could be leaked. So in particular, this could also contain information about the challenge ID. So if SKID star is leaked, you cannot hope for any security of the challenge ciphertext. So this is like an immediate issue if you consider the leakage. I mean, in a crude form, if you look at it, this would be a problem in defining security. And prior leakage resilient IB schemes that have defined security notions consider actually large ID specific secret keys to handle and allow leakage on them. And in addition, will assume either no leakage on the master secret, or some scheme assumes like the master secret is itself large and you allow some leakage on it. But our goal, recall, is to retain the feature that the ID specific secret keys are short and ephemeral. So even if you lose out on them, we want to be able to refresh security. So now towards defining security, what do we observe here? So essentially, if you note here, let's say the leakage that is allowed is from L bits, and each of this ID specific secret key is some lambda bits. then if you note here, through this leakage, an adversary can essentially get up to L over lambda, which is theta L of the secret ID, right? If I crudely calculate these many IDs, it can definitely get through the leakage. What I would want, or the intuition for the definition that we would adapt, is that essentially this is the best or information that the adversary could get. So the adversary should not get any more information than what he would get through this trivial exploitation attack, because this is simply possible. Like if I just query my leakage function, I can query these many secret key identities and get them. And this is the best that you want to say that adversary can do. So in particular, I would want my definition to say that given a L-bit leakage, you want the adversary to not break security for at least L+1 ID. Okay. And just for a completeness sake, mention the security model, but what it essentially captures is, as before, now you have like in the IB model, you get the public parameter. It also gets the keygen oracle as not listed in the definition here. And it mentions, let's say, L+1 ID, right, for which you want to define security. Recall you want to say if you get L-bit leakage, you want like security for L+1 ID, right? One more security you want in some sense. So that's what the game captures. Let's say you define the experiment for each identity, which is like the IB experiment. What my definition would capture is that the probability that for all identities you break the security is negligible. So there would at least be one identity for which you retain the security. That's the selective security notion that we adapt in this paper. So I won't have time to go into the full construction. It is kind of complex, but I can give you kind of a high-level picture of what we do. The goal was to start with something that's known and adapted in the leakage and public key encryption literature, which is of this encrypt twice, forget one key paradigm, which is used in the literature, but that cannot be directly, unfortunately, adapted to the IB setup. So we had to build a new primitive and define it, which is a big key pseudo entropy function, which is our key building block. And on top of it, we rely on techniques from prior works on leakages and encryption and reusable two-round entropy. And this gives us our big key IB with the large public parameter actually. But we want that to be short, and that we can use tricks from Laconic OT literature and essentially get our final full-blown big key IB. So this is essentially the roadmap for our construction. And the security relies on hardness of standard assumption on groups with bilingual pairing. So I would like to conclude with some open problems that are obvious. So first, our construction is non-black box, unfortunately, in the underlying primitive. So a natural question is to make essentially this a black box construction in the underlying primitive a little bit to make it efficient. And the second question, which is interesting, comes from a recent work on incompressible encoding, which is to make these keys actually useful. When you have these big keys, they are essentially there in the system and not really useful. So this work essentially shows how to make them catalytic. So if you adapting them to this work would be an interesting open problem. Thank you. Yeah.
So first of all, thank you for the wonderful talk. And there's a question of Mohammed already.
So how tight are your results? Because you say that if the adversary gets L bits of leakage, he cannot break security for L+1, but L+1 is not very tight given that we might hope to be able to argue it for L over lambda +1. So can you fill this gap?
Our work doesn't, but that's right. Like it's not tied to that extent.
Okay.
Like we prove it for L+1. Our team is able to achieve, but you're right. Like it's not tied.
Okay, thanks.
Any more questions? So.
Yeah, I'm just curious syntactically, it probably will not work, but curious if you consider that. So there is like earlier work on what is called key insulated crypto, which kind of is similar, except there is no, I guess, additional leakage allowed on I guess, a master key, but specific schemes they use kind of polynomials and things like Shamir secret sharing. And now recently, those Shamir secret sharing schemes are shown to some extent to be leakage resilient. Have you tried an approach of adapting key insulated schemes to your setting, or things kind of don't work out?
I think we we haven't explicitly thought it through, but I don't know, actually, maybe I can discuss the model with you offline to
Okay.
figure out if it fits into our work. Yeah.
Sounds good. Thanks.
So I also have a very quick question. So people also studied like block-wise infiltration attacks. Infiltration attack, as I understand, is just you can infiltrate any part of it, but maybe like a block-wise, either you infiltrate a complete block or you don't. It's like divide the entire secret key memory into blocks. Have people studied that?
Not that I know of.
Okay.
I haven't, I haven't seen any such model for execution attack.
Okay, no problem. Thank you so much. Yeah. And thanks, David, Wei, and Shruti for the wonderful talks. All right. See you guys.